Morning, class. Today is August 20th, Thursday, 11 o'clock. For those of you not in Boone, North Carolina, it's a misty, kind of rainy-ish day. Not sunny, but a good day for some organic chemistry. Uh, Today's a great day for us collectively because we get to start kind of the rhythm of this course. And one of the reasons we talked about why this course was online was to provide a certain rhythm that wouldn't get interrupted, some predictability in your life, it's really good to have a routine. And so we can kind of start to settle into that now. So what's this routine for us starting to look like? Well, you're logging on to hopefully some good tunes before class gets started. And from there, we're going to jump into some chemistry. When you log on to this video, for the 48 of you that are here, it's great that you are here because for the students that didn't attend lectures online this summer, they pretty universally failed the course. It's just that simple. For those that are here, you'll log on when you see this video. And you'll kind of start to see the story that I'm trying to tell you, not in chemistry terms per se, but just kind of in a holistic approach. I don't want this to ever seem like we're just dumping stupid chemistry on you. There's a story I'm trying to tell you. It's going to pull from things you've seen before. And so here's the story that we're kind of working on right now. And you can kind of see the stuff that we've already done. I'm going to have a list kind of just the main ideas, the heady kind of ideas that you can start thinking about when it comes to this stuff that we're covering. And for instance, we just kind of started our course in a lecture yesterday, and we said there's a lot of stuff on this periodic table, and if there's a lot of stuff on this periodic table, what stuff are we going to use in our story of this area of chemistry? And it turns out that we're going to really focus on carbon, hydrogen, some heteroatoms. Those are the nitrogen, sulfur, oxygen, phosphorus, sometimes silicon, and then the halogens. Those are this row right here: fluorine, chlorine, bromine. All of those, excuse me. And then sometimes we're going to be seeing some halogens as well. And then, or some noble gases, maybe we won't really interact with those except in reactions, but then occasionally we'll have some metals, and those are going to be components of stabilizing salts that form negative charges. And so these aren't really all that important to us yet. And then we kind of got into the idea of, well, if the atom is what brings a lot of the mass to the molecule that we're going to start to make, or if an atom is really what's unique to a molecule, what's really cool about those atoms is what they really bring to the party. And they bring to the party, what they bring to the party, rather, are electrons. And so at that point, if we know something about the atoms we're interested in, so goodbye, vast majority of the periodic table, and hello, important atoms. If we can know something about their electrons that they're bringing to the party, then we can really start to utilize those electrons to build molecules. And that's where things get really freaking cool. And as organic chemists, as me as a trained organic chemist, I can pretty much build any molecule out there. And these molecules, while you may not see them when we make them, they're everywhere. And they have some really freaking awesome properties to them. And we can design them to do amazing, amazing things. And so that being said, when we start to really look at the holistic part of organic chemistry, many people are going to tell you it's all about carbon, and carbon's the main vehicle to which we attach heteroatoms, which bring electrons that we can utilize to form bonds. And when we form bonds, we can make molecules. And we can make molecules that are insanely expensive and make bukus of cash. And so then when you log on to this video, at the beginning of this, you'll kind of see a post-it note here of these are just some of the ideas that I'm going to work with today to tell the next chapter of our story. And if I'm doing my job, we're going to get a lot of details in. But if I'm also doing my job, there is a story that you're also understanding. And let me just sidetrack from there just for 1 second. I'll warn you, I did not nail the caffeine right again. So we're excited and amped to be teaching today. And if we were together, I hopefully I just really hope that even in the short amount of time that you've seen me, you just start freaking buying into what I'm trying to put out here. I really love teaching. I'm here for you, even though it's on the other side of this stupid internet screen. But really, just buy in because this is a lot of fun for me. Moving forward, then back to kind of where we were. Here's what I'm going to work with, and at our bare basics, if you're trying to figure out when you're navigating your own personal studies and trying to get through this course, which is largely on your own with my lectures and my help, if you're looking for places to say, oh, I gotta reach out and get some help either from my lead tutor or I gotta get some help from my professor and reach out. If you're not understanding this right here, the bare basics, the story, I'm not even talking about the chemistry, what electrons are where and what orbitals. If you are lost at the bare basics when you sit down and look at this story with any component here, red flag, absolutely reach out at that point in time because you won't understand. And I can't teach you anything about how to make bonds if you don't even understand why we're doing what we're doing. And so this is the story that I'm hopefully starting to pull and cull from all of this chemistry that we're trying to put together. Now, with that being said, today's lecture and videos, I guess, are really going to focus on the electrons that these atoms bring to the party. And so what we're going to do is we're going to look at, let me just show you the notes from yesterday, and yoink. Here's the more important part here. We kind of got to some ideas of saying, where are the electrons? And we had some different representations that we were using to say, here's some electrons, here's a Lewis dot diagram of an atom, here's the electronic configuration, and here's the energy diagram. I think we called these things energy diagrams. There's a number of different names for these things, but it kind of had all these ideas, and then we ended with the question, well, if there's only two unpaired electrons in this carbon electron configuration dealio, how do we end up with 4 bonds to them if there's only 2 unpaired? And we're going to kind of bounce back and forth between some of this stuff, but what I want to do first is say, let's talk about what a bond is, and then kind of build from there into some necessity of understanding more things, which will then be the vehicle for us to pull some more information from general chemistry that we need from OChem. I try and make these lectures as question-based as possible. And right now we're sitting on a really big freaking question, which is, how can carbon have 4 bonds if there's only 2 unpaired electrons in the p orbitals? And that's a fundamentally important question because we end up with some things that are carbon that are just charcoal that we use to smoke some great brisket during football season, and we also have this carbon stuff that's buried in a ring that you use sometimes to show and demonstrate love to someone else. And so if these things exist that are worth so much freaking money, how do they have 4 bonds? And we haven't really rectified that yet. We've just posed a question. And so looking at today's notes then, let's talk about what is a bond? Question mark. And so we're just gonna we're gonna work with hydrogen first because frankly I need a little runway to just ease into this. Hydrogen, we've kind of talked about. Here's a Lewis dot structure of hydrogen. It's that H with the dot. And then we kind of said that there's an electronic configuration that would be like 1s1. For this, and there's also this energy diagram that we could draw here where we have like a 1s orbital and we've put 1 electron into that thing right there, and that's some great representations. What I want to say then is how do we get from electrons on atoms to electrons in bonds? And and simply saying what's happening when we have something like H2, which is a gas. What has happened to join these two hydrogen atoms together to make this new, well, a molecule? So we're building up from atoms to molecules, thinking tiny Legos to now something that resembles a structure. Well, if that's the case, if we wanted to use this, oh, here it is. Time to get your colored pencils and pens out, kids. So remembering that this right here is your Lewis dot structure. If we were to make hydrogen 2 gas, and we're just going to kind of look at the Lewis representation of that, perhaps we would draw a hydrogen. Let's make that an actual H. And then another dot in between those two hydrogen atoms to represent the bond. I don't really think there's anything there that I'm showing you that's too big of a stretch to say. Sometimes we would represent those two electrons, inferring that they now form a bond with a line, and suggesting that there are in fact two electrons in this line, is some assumed knowledge that we're making there. One could say that if this 1s orbital looks like a sphere, and so we're going to draw a circle on our two-dimensional space. I'm not Dr. Strange and can't conjure up some sphere for you to visualize right now, so our circle will have to do. Perhaps we could use just some visual representation of saying that perhaps if we wanted to make a hydrogen 2 gas molecule, it would be the addition of this plus another hydrogen atom's 1s electron to make an H2 molecule that is really a 1s plus a 1s together. And if we were to represent that, that would kind of be the idea of saying we've got, an electron and a 1s orbital. So something like this, and we're adding these two things together. And when we do, it would probably represent like some really good overlap. Oh, I didn't leave myself any space, but we'll put 2 dots right here. Almost screwed that up. But that would be this idea of saying, hey, that's inside that sphere is a hydrogen nuclei, and this one electron is zipping around with its electron in this cloud. And when we add these two things together, there's overlap right in this area. And that overlap is our bond. And so visually that could be our new, what we would call this thing would be, so this would be atomic orbital, and this would be an atomic orbital, and it happens to be a 1s atomic orbital, plus another 1s atomic orbital is now going to make this new molecular orbital, in which these two electrons are now occupying the space in between these two hydrogen nuclei, and that space where they're kind of shared between those two nuclei are when a bond is formed, and that makes a new molecular orbital. There's more to this story that I'll talk to you about. Emotional moment. I don't know if I'll ever be able to talk to you about molecular orbital theory, because that's an OChem 2 topic. We'll just push through those emotions. Moving forward, there's more to this molecular orbital story that someone will tell you, but certainly the idea is pretty straightforward. I can combine electrons, in the most simple form, 2 hydrogen dots together to make a H with a colon between them to suggest that those electrons are shared together. I can draw them in a line in between one another to suggest there's two electrons in there. And then kind of just the idea then of saying if an electron is in an atomic orbital, and we recognize that a 1s orbital looks like a sphere, then we're saying let's add spheres together to make a molecular orbital, and where those spheres overlap, that becomes the bond, and so this idea that I've just explained here is there's some molecular orbital theory here that we're just going to have to just package and put in a place that for someone else to help you uncover. But right now, this whole idea of combining atomic orbitals and overlapping them to form a new molecular orbital, that's your valence bond theory. And so the idea of this is kind of, and you can dive into your textbook to get a little bit more information and depth into this idea. And if you remember this stuff from Gen Chem, well, great. This is what we're calling back to. But don't get complacent with your understanding from Gen Chem just because you're recognizing what I'm talking to you about now. Because we want to be able to pull from Gen Chem, but when we pull the specific information we need from general chemistry, we have to be able to pull it into our organic chemistry lexicon that we're going to use, but we have to have it mastered. You can't just be like, oh, I saw it in Gen Chem, now I can do it in OChem. No, it's not the matrix. You haven't been plugged in and all of a sudden know this is happening. You have to take that stuff and these tiny bits we're pulling from, you have to master it. And so what are the components of valence bond theory that we really need to master or remember from Gen Chem? Atomic orbitals overlap to make molecular orbitals. Yeah, I'd say more overlap equals stronger bond. And we'll talk more about that in some of the examples I get to later on. Cool. And so if we can kind of pull together this information and say, here's some information about just bonds in general and how do we get some bonds put together. Well, it appears like we just start to overlap orbitals. And that's not too big of a stretch. I don't think I've lost anybody yet this morning with this idea. Let's talk one more thing that's really nuanced. A lot of organic chemistry is symbolism as well. Look at this shit that's on this paper right now. Profanity number 2. Okay, we're two. We're just not going to be able to keep track of that. But look, just look at this. A dot. What the heck is a dot? Well, apparently a dot here is an electron. What's this? That's an arrow with 2 heads. What's this? That's an arrow with 1 head. Well, this 2-headed arrow means increasing energy. But then when we look at this stupid picture, there's a 1 barbed arrow right here. Look at all the symbolism that's embedded in this stuff. This could be a double bond, or this could be an equal sign. Look at this crap. There's so much that we kind of have to get used to seeing. Here's one thing that's very unique to organic chemistry that is worth noting, and it's this right here, an arrow. This single barb, we're kind of thinking more of a fish hook arrow. That single barbed arrow means 1 electron. And this kind of means 2 electrons down the road. Okay, a double barbed means 2 electrons. And so it's just something that you might have probably seen, or maybe even in your notes, you'd felt the inclination to just draw a regular normal arrow right here. And right now in this course, on this next quiz on Sunday, on this upcoming examination, you're not going to get any points docked. But just if you did notice the fact that this didn't look like I finished something, that's actually deliberate, and here's why, and something that you'll start to have to recognize really soon when we talk about reactivity. This is deliberate, just something to note. So moving forward then, I wish we could just talk about hydrogen. But that's kind of elementary. That's kind of not as fun. And we have to talk more about some larger molecules and bigger molecules, because that's where all the real excitement is. And so now we kind of have to take a look at saying, well, let's look at carbon again. Carbon. We had designed this energy diagram that suggested carbon consists of a 1s orbital. That s looks really horrible. But then a 2s orbital, didn't get any better there. And then it had this degenerate set of 2p orbitals, of which you would have some in the x, some in the y, and 2p, some in the z direction. These are Cartesian coordinates pointing in different directions. And owning the fact that when you have degenerate orbitals, add all of those orbitals up together and you get a sphere shape from them. And so you have one kind of dumbbell set that is the y Cartesian coordinates like this. You have one that's in the x-axis like this, and then you have one that's in the z-axis, which I'm going to have to draw a little bit like that, just to suggest that it's kind of pointing this way outside of the paper, kind of at you. And so you have these different, but if you put them all together, you put 3 dumbbells together and look at the overall dumbbell shape of the combined dumbbells, and you kind of have a spherical shape if you stretch your mind. And just remembering some other artifacts of this too. I mean, what does this sphere even mean? Well, this sphere means that there is the line. I mean, again, this is some cool stuff, but we're looking at weird shapes. What do these weird shapes mean? Well, what does the line mean? The line means that there is and I'm just going to write like 98% chance of finding, running out of space, finding an electron inside this region, demonstrated by that line. So where would an electron be around a hydrogen atom? So here's that hydrogen atom, and it's got that 1 electron. And if we draw a circle saying, hey, that not a bad circle. If we draw a circle around that hydrogen and say, where's that electron around that hydrogen? The answer to that question is 98% of the time, it's going to be located inside of that circle. That's what this kind of stuff means. And so the electron, so when we populate these orbitals with the electrons around carbon based on the looking with the arrow over here, based on this periodic table, 1s, 2s, 3, 1s1, 1s2, 2s1, 2s2, 2p1, 2p2. These electrons are inside of orbitals that look like this, and then the idea is that this electron right here in the 2py region is restricted in this dumbbell shape 98%. And if you were to go 99, the dumbbell would be a little bit bigger. And the idea is simply saying that 98% of the time or 90% of the time you're going to find the electron somewhere in this region zipping around in the space that looks like a dumbbell. Fundamentally a really cool idea. And we can never have 100% certainty of where that electron is, because the idea really here is that an electron that is on the pencil that you're using or pen that you are using in your hand has a probability of zipping right in front of my face at that moment in time. And so that kind of gets into some really heady things about where are electrons and quantum mechanics, but just know that the interval that we're giving it is saying if you were to just take a Polaroid picture, I don't even know if you know what those are, a selfie of this atom was to take a selfie, and all of a sudden you'd all this be able to see where that electron was. You'd find it when you took a million selfies of that atom, that this one electron would be somewhere in that dumbbell shape 98% of the time. Or if you want to use the Anchorman type definition, the electron around this hydrogen, 98% of the time you're going to find it here all of the time. Inside that circle. And so then the idea would be, so if we were just to, this is not, we got to kind of jump into hypothetical world, because we have to rectify this idea that hydrogen, or not hydrogen, but carbon can have 4 bonds around it, but we only have 2 unpaired electrons. But before I want to dive into how we end up creating a system where we have 4 potential unpaired electrons, before we jump into that, I just kind of want to remind you of how valence bond theory now applies to something that doesn't involve 2 spheres coming together. And it's not really that big of an extension of something to get to. But if we were just to say, let's take the electron that is in the 2px, and so just let me write some space over here, so kind of a sidebar. If I have, so valence bond theory, overlapping more complex orbitals. And then the idea here is overlapping them doesn't have to be any more complex, but we just got to visit the idea. If I was going to add the 2px orbital like this from carbon in a carbon-hydrogen bond with the hydrogens 1s orbital like this, then our new molecular orbital that would exist would be this plus this together. And so then those electrons could exist in here. If I had drawn that a little better, I would have centered it a little bit more. Hopefully you're a better artist than I am. But you get the idea that this is overlap that is certainly going to form a bond. It's a good bond. It's in the ring that Beyonce sings about. And so it does exist. But just remember that when we had our hydrogen type bond, that would have, brand new pen, that would have been something like that. And so this would have the hydrogen, so the sphere overlap. There would be more overlap there than you'd find in a p S overlap type orbital, and so you'd expect this green blue overlap of a hydrogen 2 atom like this right here to be far stronger because there's more overlap than really 1/3 of that sphere overlapping with the other sphere here. So just keep in mind there's some more stuff that's buried underneath these pretty little pictures. The idea here, and this is why I love these videos for teaching, is you can rewind this idea and just go back in the Wayback Machine 30 seconds when you're watching this again, and just keep watching that over and over to really drive home that idea of, yes, we have these really pretty pictures here that we can use to demonstrate some very complex ideas. I mean, you guys are doing molecular orbital theory and quantum mechanics when you do these pictures, but let's not get lost in all of that stuff and remember some of the more core concepts, which is we are overlapping atomic orbitals, overlapping them to form bonds, but in doing so, when they overlap, the amount of overlap that occurs increases the strength of that bond, and that's why in the end, the more overlap, the stronger bond. Don't forget that the p orbital is only 1/3 of the potential sphere that could overlap, and so it's going to be weaker because there is less overlap, and hopefully you see that in that picture. Now, from this, I could hypothetically, from this, I could suggest that I could buy the case that in this state, I could buy an idea where this carbon atom could potentially bond to 2 hydrogen atoms and then feature 2 lone pairs of electrons. And I could really get on that idea based on the information that we have right now. And hopefully that's okay for everyone. We're going to build from this, and some of you are brilliant in this class. I guarantee you're smarter than I am. And you can already see where we're going with this, and you want to run ahead. And good if you see where this is going, because that clairvoyance you have means that you have solid foundation from general chemistry that you're applying, and you can kind of see where these themes are. If you're completely lost with everything I'm doing, you have to reach out to me right now. No, not right now, I'm busy. But like after class, and through email. And if you're kind of getting this stuff, you say, oh, I've seen this before. I can see where he is right now. I'm not quite sure where he's going. Great. That's right where I need you to be. And so then I'm doing my job of kind of helping pull you along in a sense and filter and focus all of the stuff you got from Gen Chem into something we're using for OChem. Let's just briefly talk, and here's where we can really use some beautiful, beautiful colors to increase our understanding here. If I were to draw this, again, this is just like a red flag right here. Again, hypothetical model based on info provided. This isn't right, but this is certainly solid for the understanding that we have based on this information. Unpaired electrons can overlap with other stuff, and then they overlap with other stuff. It makes new bonds, and so I've got 2 of those, so I got these 2 bonds, and so this 1 electron right here, if I were just to redraw this, I can do an even better job here. We would say, hey, this electron was probably used right in here. And this electron right here in light blue is probably being used. I don't have it. There it is. Right in here. And then perhaps if we were to go even a little bit further, pink, maybe these 2 electrons. There's some ambiguity here, people, but perhaps there. I have committed to a circle and then fully committed to a rectangle after that, so that's that shape. And then this one right here, perhaps these electrons. I'm just trying to get you the idea of just saying, hey, we've got some information that we've used before from Gen Chem. We're trying to assemble molecules based on unpaired electrons. Here's a reasonable proposal for a structure based on that relevant information. And the only thing we have left to do, we are 34 minutes into this lecture, and he still hasn't even answered the question from before, but it's still pretty basic and straightforward. How does carbon have 4 bonds? But if we can understand overlapping, if we can understand where unpaired electrons could be used, then we can absolutely, without any question, running out of desk space, start to understand how carbon can have 4 bonds. And so let's take a look at the energy diagram again. I'm going to draw things just a little bit more pronounced here. Here's the 1s orbital for carbon that we had drawn 2 electrons in. The 2s orbital, which has 2 electrons in it, and then you have this degenerate set of 2p orbitals, arbitrarily x, y, and z. So this would be carbon. It turns out that we can use, and you've seen this before, we could use hybridization to promote electrons from different energy levels to essentially make hybrid orbitals that have the properties of each combined atomic orbital that then allow us to form new molecular orbitals. If we were to take and combine all hybrid orbitals together, none of that made sense. If we were to combine all of these atomic orbitals together, we would get hybrid orbitals that are all of the same energy, and we would then have 4 unpaired electrons. And if unpaired electrons are really the ingredients that we need in order to make new bonds, well, that certainly is a very reasonable way of being able to justify how carbon has 4 bonds. It's a theory that we can use to explain something that we know to be true in nature, but we can't explain with our very fundamental basic understanding. So this process is called hybridization. And so you have a hybridized set here. And so what can I say for this? You have combined, hybridization then is combining atomic orbitals to make hybrid atomic orbitals. And hopefully if this color thing is working for you, excellent. I really primarily use one dark color for the notes, and then I try and toggle between orange and red to supplement some of the important information here. And so you can kind of see the core notes and then some ideas that we're peppering around these. And so let's identify these things right here. All of these I'm going to put the stars here. Here you have a bunch of atomic orbitals that you have. You have a 2s orbital. You have a 2p orbital x. You have a 2p orbital y. And then you got this 2p orbital z. Oh, I see what happened there. And then you've combined those to make new hybrid atomic orbitals, and now you have 4 of them that have some characteristic from the p section, and then you've really ballooned this other half of that p orbital with all of that s characteristic, and then these right here become your hybrid atomic orbitals. You never touch the 1s, so that still stays as its lone that lone orbital that is not hybrid. Some other things to note before we take a quick break. Oh yeah, so the picture math. The idea here is that you've taken this atomic orbital from the 2s and you've added it to the 2p, and so one side of this then has essentially just grown and ballooned. So this side is the same right here, and then the other part got real big like that. And that became what your hybrid orbitals look like. And then just some other notes of importance. You remember then that the energy, keep in mind, if this is energy on the y-axis, then the energy of these hybrid orbitals is somewhere, we'll just pick a different color here. The energy is somewhere between the energy of the atomic orbitals. Cool. And I think now it certainly becomes obvious to me that we have created an instance where we have 4 unpaired electrons, and those 4 unpaired electrons could certainly be used to form new bonds to other atoms. And let's just follow this through. This guy right here could be this electron right here. This electron right here could be this one right here. This one right here in pink could be this one right here. And some darker green. Oh, new pen. That might have not been the best choice, but I think you guys can see. That could give rise to that those electrons that would eventually then be used to form some new bonds. I need a break. That was a lot. And so let's just take a 5-minute break. And when we come back from that, we're going to continue this lecture. So we'll be back in just 5 minutes.